we'll discuss the case of torque on a rectangular current loop when placed in a uniform magnetic field. So you might have learned about current loops, so sometimes also referred to as armatures. So an armature is basically a copper wire which is bent into the shape of a loop. So the loop can be circular or a loop can be rectangular. It could take any shape, but it's basically a pathway where you force the current to move in a certain shape. And right here we are considering a rectangular armature. So in the figure, as you see, a rectangular armature connected via an armature brush contraption has been connected to a potential source. So whenever the switch is closed and current is made to flow through this pathway, the rectangular pathway, obviously we know that flow of current through a current carrying conductor generates a magnetic field, and that generated magnetic field will now interact with the magnetic field in which this loop has been placed. So let's discuss this whole scenario in two stages. So the first stage we consider is the case when the plane of the loop is parallel to the magnetic field. So if you consider the north pole and the south pole of the poles of the two magnets that are placed here, we know that magnetic field emerges from the north pole and terminates at the south pole. So the magnetic field is moving in this direction. So this is the magnetic field. It is moving parallel from one magnet to the other magnet. So if I were to see the whole contraption from this side, it would look something like this to me. So this is the loop, current loop, and the magnetic field is in this direction. We will have field lines of the magnet flowing this way, emerging at north pole and terminating at the south pole. So this will be the direction of the magnetic field, and the plane of my armature as viewed from here is this. Now the first stage that I am considering is when the plane of the armature is parallel to the magnetic field. So this is the first stage that I am going to consider. Now I can divide the whole armature into at least 4 distinct sections. So if I name the 4 corners as A, B, C and D, I have sections AD, AB, BC and CD. Now if you notice, BC and AD are current carrying wires which are parallel to the magnetic field. So obviously, since they are parallel to the magnetic field, there would not be any force that would be generated on them. So then we are only left with AB and CD. So let's consider the force on AB. So the force on AB, we know in our previous discussions, the force on a current carrying conductor of length L carrying a current I when placed in a magnetic field, external magnetic field of strength B, is given by I into L into B, the product of the 3 entities. So the same way, FAB I can calculate by taking the strength of the current, which is I, which I have denoted as I, flowing through the armature, the length of this section of the armature. So the length over here, I have taken it as some small letter B into the magnetic field, which is capital B. Now, the force acts in a particular direction. So if I want to find out the direction of the force that's acting on this particular length of the armature, then I have to use the Fleming's left-hand rule, where my middle finger gives the flow of current, so I align it to the flow of current, and the index finger points to the magnetic field, which is in this direction, so I align it this way, and what you'll see is that the thumb, which shows the force of the magnetic field acting on this particular length of the armature, is something that goes into the board. So in reality, if the armature was plain over here, magnetic field would be going in this direction, current will be going in this direction, so the force will be acting downwards. So the force on this particular section is acting downwards. So this is the direction of FAB. Now let's consider, so I'll just say downwards. We'll come back to that. Now if I want to consider the length CD, so again the current flowing is I, the length is B, and the magnetic field is capital B. What's the direction? So current is now flowing this way. So I keep my finger this way, magnetic field is this way. Now you will see that the force is out of the board. So in this direction it would be upwards. So the direction here, while if AB was downwards, FCD is upwards. Now if you look at the right hand sides here, they are both the same, which means FAB is equal to FCD when I consider only the magnitudes. And since they are in opposite direction, one is acting downwards, the other is acting upwards, they cancel out each other. But what happens is that while the forces cancel out each other, they are acting some distance away from the axis of this armature. This is the axis of the armature. They are acting some distance away. So if I take the width of this armature as A, this force is acting halfway to the right, and this force FAB is acting halfway to the left, and they are acting in opposite directions. So when two equal forces act in opposite directions at some distance away from the axis, they create what is called a torque, something that you learned last year. So they create a torque. So if I want to calculate the torque, remember it was represented by the letter tau. So the torque is given by the force multiplied by the perpendicular distance from the axis. So FAB into its distance from the axis, which is A by 2. Similarly, the other torque, if I add it up, is FCD into A by 2. Now FAB and FCD are same forces, so I'll just represent it with capital F. So F, if I remove common, it's A by 2 plus A by 2, which gives me FA. So torque is given by F into A. Now if I replace the force F with the right hand side value, I get I, B, capital B into A, this A. And if I simplify this, I take capital I and capital B to one side, what I am left with is A into B. So what is A into B? A is the width of the armature, B is the length of the armature. So A into B, I can replace it with the multiplication of A into B gives me the area of this armature. So it is I A, which is the area of the armature, where capital A is equal to A into B. So torque is given by the current into the area of the armature into the magnetic field. So the product of these three entities gives the net torque on the armature when I consider the case where the armature is parallel to the magnetic field. Now let's consider the second stage. So in the first stage, say if this was my armature, in the first stage we consider the case when the north pole of the magnet was at this place and the south pole was at this place, and the plane of the armature was parallel to the magnetic field. And if this was AB and this was CD, the force acting here, FAB, was downwards and FCD was acting upwards. So this causes the forces to cancel out each other, but the net result is a torque which causes this armature to start moving in this direction along the central axis. Now at this position, if I were to define a couple of additional specifications, we said the magnetic field acts from the right to the left, right? Now as the magnetic field works in this direction, the normal to this particular plane, let me consider that as M, which is acting downwards. So the angle between this and this is 90 degrees. It is 90 degrees. Now as this starts turning this way due to the torque that's acting, the normal at this position, let's take this new position, at this position the normal to the plane or the loop, plane of the loop is this, whereas magnetic field is still acting in this direction. So if I consider this angle between the magnetic field and the normal to the plane of the loop, I consider that angle as theta. At this position the angle was 90 degrees. At this position that angle has reduced to some value between 0 and 90 degrees. So initially magnetic field was acting in this direction and the plane of the armature was also in this direction. So this is the normal to this plane. So this angle was 90 degrees or pi by 2. Now as the force here was acting downwards and this was acting upwards, say a second later the armature might be in this position. Magnetic field is still acting in this direction, but the normal to this plane is now here. Now this angle is theta, which is less than pi by 2 or 90 degrees. Now if I consider the forces acting here and here, they will still be equal. So force AB will be equal to force CD, which will still be I into B into capital B. But if I calculate the torque will be given by force AB into, it's not just A by 2 as it was in this case, but since they are acting at an angle, it's A by 2 and the sine component, sine of theta, plus FCD A by 2 sine theta. So when I combine these two equations, I get FAB and FCD. If I consider it as F, so F into A by 2 plus A by 2 sine theta. which gives me, replacing F with IBB, I get I capital B, A by 2 plus A by 2 will give me A into B into sine theta. So I get I A B sine theta, which means to say the torque now acting on this armature is less than the torque that was acting on the armature when the armature was in this position, when it was parallel to the magnetic field, or when the normal to the plane of the loop was at 90 degrees with the magnetic field. So the torque now is less in this position. So as it moves further and further and further, eventually you reach this position. At this position, you will have this angle which is reducing. At all stages, it is reducing, and eventually, so if this was position 1, this was position 2, eventually you will reach a position where the magnetic field is in this direction and the armature is like this, and the normal to the plane of the loop is parallel with the magnetic field. M is parallel to B. So at this point, when the armature is perpendicular to the magnetic field, or in other words, the normal to the plane of the loop is parallel to the magnetic field, angle theta is equal to 0 degrees. That means it has reached its equilibrium position. Torque becomes absolutely 0 when theta is 0, because sine 0 gives you 0. So at this position, it's the equilibrium position. So at this position, the loop will be balanced, but slight deviation on either direction and a torque starts acting on it and it starts rotating again. So the maximum torque is when it is parallel to the magnetic field. Torque is 0 when it's perpendicular to the magnetic field. When the normal to the plane of the loop is parallel to the magnetic field, theta is 0 and torque becomes 0. Now, this can be expressed by combining I and A. I and A can be combined to define what we call a magnetic moment. So a magnetic moment is represented by capital M into B sine theta. So since if we want to represent it vectorially, we can then give it as the vector product of magnetic moment and the magnetic field. So tau, or the torque at any point, is given by the vector product of the magnetic moment and the magnetic field. So tau, we just recall, is given by the vector product of the magnetic dipole and the magnetic field. Some textbooks also use the small m. You can use either one according to your convenience. Now what does this remind you? This also reminds you of the torque in the case of an electric dipole we had studied in the previous chapters. So there, the electric dipole was represented with the letter P multiplied vectorially with the electric field to give the torque on it. So this is very similar to that. Now even if you have a coil of n number of wires, n number of turns, then M, which was the product of I and A, will take the form of NIA. If this applies for one loop, this applies for a coil of n loops. So this still holds valid.